Rebecca Tyson. Her title is CHANS. I hope I'm saying that properly, or you don't do it individually, CHANS, with options dynamics. Rebecca Tyson is Professor of Mathematics at the University of British Columbia, UBC Okanagan in Kelowna, British Columbia. Her work lies mainly in the area of theoretical ecology, specifically population dynamics and dispersal of population in variable landscapes. She's worked on questions related to predator-prey cycles, mountain pine beetle dispersal, pollinator services of honeybees, and human-bear interactions in interface communities like Whistler, BC. The models she uses include ordinary and partial differential equations, as well as individual-based computational models. Recently, she's become interested in the dynamical interface between ecology and human options, as the latter is a critical component of conservation work in the former. The ecology opinion dynamics interface is closely linked to the epidemiology opinion dynamics interface, and so the second interface has emerged as an important thread in Dr. Tyson's work. So this is very interesting, and as we discussed yesterday, this sort of comes into this whole area of the One Health approach. So how we look at all the entire kind of ecosystem approach, and also how we can learn and bring in more from biology and nature as we all interact together. So thank you, Rebecca.
Thank you, Sarah. And thank you, Roxanne and Shana, for your presentations. They're very interesting, and coming at this problem from we think about opinions and behavior as being in the wheelhouse of psychology, and here I am as a mathematician trying to put it in a model. And so my opinion dynamics are perhaps rudimentary, but we know that opinions change through time. And we've been watching through this pandemic how they affect the evolution of the disease through time. And so if we're going to understand how these two processes work together, we really do need to try and start modeling them in some of the ways that I'm talking about today. So what I'm presenting here is my, this is the route I've taken with some colleagues. We're trying to introduce the idea of opinion dynamics to diseases and model the two processes together as a dynamical system. Now I know we're running over time. Slide stuck, that's interesting. We didn't check this. Okay, wait. Let's see what it's going to work now. Now it's working. Okay, sorry, the chat window is stopping it. So these are my collaborators. I've been working with Bert Baumgartner and Steve Crone from the University of Idaho, and these are two students who've contributed a great deal to the project, Noah Marshall, who's now at McGill, and Stephanie Hamilton, who is doing graduate work at UBC Okanagan. They were both undergraduates at the time they worked on this project. So our main questions were the following. So how do opinions evolve in a population? And then once we've got that figured out, we can couple that to disease dynamics and ask, how do opinion dynamics alter the time course of an epidemic? And we assume that opinions evolve as a result of meaningful interactions between people. So this is the way we chose to model opinions. We gave each individual an attitude from an attitude spectrum, which goes from -L to +L. And so we have an L can be any value. So here's an example where we've got opinions that are ±1, ±2, out to ±L. Note that we don't have a 0. That was a purely mathematical problem, and we had to eliminate it because when you start multiplying things by 0, things go to 0, and so we just didn't know what to do with 0. So you can't be completely neutral. Everybody has to be either a little bit one side or a little bit the other. Now, given a particular attitude from this attitude spectrum, then you belong either to, you can divide that spectrum into two halves, the plus half and the minus half. And so that's the opinion is given by the sign, and then the strength of the opinion is given by the magnitude. Now, I tend to use the word opinion interchangeably with attitudes. So hopefully it doesn't get confusing. But this is basically, this is the breakdown of how an opinion is formed. All right, now we have to update these attitudes and opinions in the model. And we chose to use two factors, influence and amplification. So influence, we assume that the likelihood of an individual's opinion affecting others depends on the strength of that opinion via what we called an influence function. And here are three possibilities. We don't know what this influence function looks like, but a few possibilities are that all attitudes have the same weight. It doesn't matter what the attitude is of the person you're talking with. Any attitude would have the same level of influence on your own. We could give more weight to extreme attitudes. We called that linear influence. Or we could give more weight to moderate attitudes. Maybe extreme attitudes are off-putting and it's actually moderate attitudes that have more influence. And we call that collinear influence. We also looked at quadratic and co-quadratic influence, where the increased influence at the extremes or decreased influence at the extremes goes up faster than linearly, but there isn't time. So I'll just show you the results for linear and collinear, or talk about those. Okay, so amplification was the other component we looked at. This is well known in the psychology literature. It's the tendency to become more entrenched in one's current opinion when interacting with another individual of the same opinion, regardless of the strength of that opinion. So before we look at the figure, what this means is that if you take two people who are very slightly on one side of an issue, so maybe they're both at +1 in their attitude, and you let them talk to each other for a while, they will emerge from that discussion being more entrenched in their opinion. So they would have moved from a +1 to perhaps a +2. In spite of the fact that there was nobody in the room that had that stronger opinion, their interaction will create this increased or this movement toward the extreme. It doesn't happen if you get one person slightly on the plus side, one person slightly on the negative side. They don't become, that's not amplification, that's a whole separate process that we're not including. So we just have the amplification, or it's also called my side bias, where if you interact with somebody with the same opinion, even if it's different, that you will become more entrenched. Okay, so mathematically, the way this works, without amplification, if a +2 attitude interacts with a +1, and in the model you have to decide who's moving, who is influencing and who is being influenced. So the purple one is being influenced and the green one is doing the influencing. So a +1 will influence a +2 to move, and we assume that there's a tendency to move together. So that the purple individual being influenced will tend to move toward the +1. With amplification, however, the movement's in the opposite direction. So this +1 influence makes the +2 more entrenched and becomes a +3. Okay, so those are the components of the model. And if you put that all together in an agent-based model, you get results that look like this. So we have a big grid of agents who aren't moving, so they can only talk to their neighbors. We start with a uniform distribution of attitudes across the population. The first thing we see is centering. So the attitudes all move toward the center. And then we see a gradual movement out towards a polarized state. So this peak in the middle is starting to split. Here now we've got two peaks, and eventually we end up with this bathtub type distribution, which moves very, very slowly, hardly changes at all. And then in a grid, you can end up with structures that are very stable and won't change. So any diagonals will go away, but if you end up with the vertical strip like this, it essentially lasts forever. And this is with a level of amplification at 0.07, which is fairly small. Okay, so these are some of the results aggregated into plots, where we see this is the centering I talked about. And if there is no amplification at all, then the centering stays. So that's the stable state. As soon as you add any amplification, this initial centering goes away and you see the extreme opinions growing. And the more amplification there is, the faster that happens. So the smaller the swing to the center, and the faster the swing to the extremes. The influence function can counteract this effect to some extent.
Clarifying question?
Question?
Sorry.
Yeah, sure.
Yeah, there's only two opinions. It's just the strengths that are varying, correct? There's positive opinion, negative opinion.
Yes.
It's just signum. It's not that extreme opinions are appearing. It's just that in the strength with which people adopt one of the two opinions is increasing.
Right. So I should have said extreme attitudes.
Okay. Sorry.
Okay. No, that's fine. So the linear influence function accelerates the growth of the extreme attitudes, because of course there's more weight given to the extreme attitudes. But collinear influence, if the amplification is low enough, collinear influence can counteract that effect. So if the moderate attitudes have more weight, then we can remain at a centered state. Now, we want to put this in an ordinary differential equation model. So we have to define our variables and parameters. So we let x sub a be the global frequency of attitude A at time t. P sub a is the fraction of interactions that result in amplification. So we assume that amplification isn't on all the time. So that's what those values of amplification being 0.7 or a 0.07 or 0.05, that means that amplification isn't always in play. So whenever there's an interaction between two people on the same side, then we assume that amplification sometimes will occur and sometimes it won't. And then WA is the frequency dependent weight of attitude A at time t. And so we're taking the, so IA is the influence function. So this is the influence accorded to attitude A. And then we divide that by the influence accorded to each attitude multiplied by the proportion of the population that has that attitude. Okay, and then if we look at the case L equals 2, we can write the equation down. So this is one of the equations. This is for the -2 subpopulation. So we have here all of the interactions that result in an increase in that population. So if a -1 interacts with it, so if a -1 is being influenced by a -2, then the -1 individual will become a -2 with this weighting. And then if a -1, so here's the -1, is being influenced by a -1, then if amplification occurs, then the -1 will become a -2. Those are the two ways you can get a new -2. And then these are the interactions that result in losing a -2. And we assume that there could only be one step at a time. So this is what the full set of equations looks like. So we have an ODE for each subgroup. And then again, if you count up the interactions that can occur and which ones will result in an increase or decrease in the population, you get a system that looks like this. And if we run the ordinary differential equation model and compare it to the agent-based model with mixing introduced, we see that the comparison is quite good. The colors here are different from what they were before. So we've got, anyway, we'll see more colors later. So we've got a good match between the two. This is with a very low level of amplification for this figure, so that we could see things going on. When the amplification is larger, things happen so fast. Okay, so then what we want to do is we want to couple this opinion dynamics model to a disease model. And I'll be really quick about this part because I know we're running late. So I think most people listening, or a lot of people listening, are familiar with the disease model idea. So really all we've done that's novel is now we've got this opinion dynamics that are happening as well. We were interested in the case of reversible prophylaxis. So we're not looking at the vaccination case in this study. And reversible prophylaxis is stuff that you can choose to do or not do at any point in time. Sorry about that. And we'll just ignore that noise. Okay. So then what we've got going on here is we have our opinion dynamics model in this part of the diagram, and then we're coupling that to the disease part. And so we assume that the opinions only exist in the susceptible population. Ideally, they would exist in all parts of the population, but it made the system too big. So we started with opinion dynamics in the susceptible group and then not in the infectious or recovered group. And the model is otherwise what you would expect for an SIR disease model, just that the transmission coefficient here, these betas, they depend on the level of prophylaxis. So we assume the plus side is non-prophylactic and the minus side is prophylactic. So we had a Q parameter where as you go from prophylaxis, which has a very low transmission rate, up to non-prophylaxis, there's a factor Q at each step. And then these are our influence functions. Before I only talked about the linear influence function. We don't have the collinear here. In this study, we looked at linear, we looked at saturating, we looked at fixed order saturating. Notice that this, if you just use a naive mathematical function, you end up with this switch in order for very low levels of infection. So we created a new function that didn't have that switch in order. And then here's our reverse order. So it's a reverse order saturating, where now the more central attitudes have a stronger influence. Okay, so the equations again, as you would expect, the results. So we were interested in how the initial level of prophylaxis in the population affects disease outcomes such as final size, peak size, and duration. And not surprising, the more prophylaxis there is in the population to start with, the lower the final size or the peak size. And after a couple of years of COVID, we're all familiar with the fact that if you flatten the curve, you also stretch it out. And so duration goes up. It starts crashing when that reproduction number starts getting very close to 1. And then finally, the duration will shorten. We can also ask how the rates of the opinion dynamics and the disease dynamics interact to change final size, peak size, and duration. And I forgot to mention on the previous slide that these different curves are due to the different influence functions. They become more important in this scenario where now we've varied the rates. So now in the first row, the opinion dynamics are faster. And in the second row, the disease and opinion dynamics are faster. So if the opinion dynamics alone are faster, then final size goes down, peak size goes down, but duration may or may not go down, depending on the influence function. But if the disease dynamics are faster, we get a very different result. And one of the interesting things here is that this case, I think corresponds to, if I remember, that's reverse order saturating. So now if the moderate opinions are more influential, then you can end up with this scenario where the final size really doesn't go down as the initial prophylaxis level goes up. And duration is just going up, partly because it's harder to get to that R0 = 1. when the disease dynamics are that much faster. We also looked at polarization. This is another thing we have access to with a model like this. Polarization, there are papers out there that talk about polarization. The trick is you have to decide how polarized a group is. So if they're divided 50-50 on an issue with everybody at the +2 and -2 ends, well, that's completely polarized. But what if it's 30-70? What if it's 20% still in the middle and others on the edges? Okay, so we have to figure out how to do that. This is an equation we pulled from the literature. So the level of polarization here, according to this function, only depends on the populations at the extreme ends of the attitude spectrum. We multiply the proportion at each extreme, but then we're also interested in the difference. So 50-50 at each extreme is different from 70-30 at each extreme. And so that's what this term is capturing here. So this term is a discounting. It's equal to 1 if they're 50-50, and then it decreases as, you know, the proportion at one end starts to go up. And so if you plot this function, you end up with these curves. This part doesn't make sense. So we have the proportion non-prophylactic and the proportion prophylactic. This is where polarization is. That's 50-50. And so they're evenly divided. And then as we move to the edges, where, you know, one side is starting to gain more over the other. And so along any one of these curves, the level of polarization is the same according to this function, but the way that population is distributed is different. And so these would all be polarized on one side, and these would be polarized on the other side with different levels of polarization. And then you can ask, how does that initial polarization affect your final size, peak size, and duration? And if everybody's distributed according to the green, we get these cases on the bottom here. So final size and peak size are minimized if the polarization is towards prophylaxis. So that's not surprising. And same if they're polarized towards non-prophylaxis, we get these red ones. So final size and peak size are larger. But each, you know, a given level of polarization will give a different final size depending on how that population is divided. Duration is more complicated, where the initial prophylaxis level can lead to either a larger or smaller final size, depending on the level of polarization. Okay, so we find that opinion dynamics, if you add them to your disease model, they have a dramatic effect on final size and peak size. The initial conditions matter, they make a big difference too. An increased weight to moderate opinions can counteract polarization, and an increased weight to extreme prophylaxis is necessary to reduce epidemic severity if disease dynamics are fast. There's a lot more work to do here. Our model for opinion dynamics is really quite rudimentary. And so I look forward to seeing a lot more work in this area where we are incorporating some of these other behaviors that Roxanne and Sanya were talking about. Thank you.
Thank you so much, Rebecca. That was absolutely fascinating.